Hey Chem30, so I'm homesick today, but I didn't want to waste a class, so I'll create a quick video here. We're just going to finish looking at voltaic cell potentials and then take a quick look at corrosion. So here's the last question in the notes there that we didn't finish from yesterday. So it says, what is the table of relative strengths in oxidizing reducing agents based off of these measured cell potentials? So essentially they are giving me three different cells here, all with their different, cathodes and anodes. And I need to figure out a similar table of half reduction reactions that I could find in my data booklet. Now, if I go in my data booklet, lead is in there, acidic dichromate is in there, copper, that's that inert electrode, but these elements here are not in there. So I'm going to have to do some problem solving in order to figure out what would be the highest oxidizing agent and what would be the lowest or highest, I guess, reducing agent. So this is what they give me. I would just examine this cell at a time. They tell me here, right, that this is the negative electrode, so that is my anode. And this is the positive electrode, so that is the cathode. So I don't really need to do any work here because obviously lead is at the anode, so it's undergoing the loss of electrons, and chromate is at the the cathode, so it is undergoing reduction. So based off of my data table in the booklet, I know that I have these two reactions, where chromate would be the strongest oxidizing agent, and lead would be the strongest reducing agent, and there are their assigned voltages based off of the data booklet. Now when I go look at this next reaction here, or this next half cell, and I go to try and find either of these in the data booklet, they do not appear in the data booklet. So I'm kind of left hanging here. There's nothing I can do with that middle cell. So I'm going to go look at the next cell and see if there's any information here that I could use that could help me figure out maybe what the voltages of, or the electrical potential of this half cell is, that could help me figure out this middle equation. And we already know the electrical potential of lead. So we just use the formula that we had yesterday, where the total electrical potential of the cell is equal to the electrical potential of the cation minus the electrical potential of the anion. And so the electrical potential of the cell, according to this chart, is 1.29, so I would put it right here, is equal to the electrical potential of the cathode. Well, they already told us that this side is the cathode, so the lead cell half reaction, the voltage for that is negative 0.13, so I would put it there. And then I just need to solve for x to figure out the electrical potential of the anode. So if I add 0.13, add 0.13, and then I would have to divide by -1 in order to get rid of the negative on the x. I get a voltage of -1.42. So then what I would need to do is create the half cell reaction between here and place it accordingly. Well, because it has a lower voltage than my lead, I would place the reaction below it in my makeshift half reaction table that I'm creating. Then, because I have this information, I can use that here. And so once again, I don't know the voltage of this. It's not in my data booklet, but we have figured out what the half reaction of this cathode is now in the cell. So once again, I use the formula. I know that the total electrical potential of the cell is 1.29 based off of the information given to me. I know the electrical potential of the cathode now because it has switched sides. It is negative 1.42 based off of the last question. And I'm just trying to solve for x. So I would add 1.42 again to either side. Ooh, my goodness, sorry. Same thing here. And then divide by -1. That would give me, if you can see through my ink there, a electrical potential voltage for this half reaction of -2.71 volts. So again, lastly, all I need to do is place this on my half reduction table here, half reaction table, And because it has the lowest voltage, I would just place it below the previous reaction that I created. And so there is my table. I should have equilibrium arrows going both ways because the reaction could proceed in either direction. The strongest reducing agent then would be this, and the strongest oxidizing agent would be on this side. Again, any type of these questions, you're probably going to have to do some problem solving using your formulas here. And some of the information will be given to you, while some of it you need to problem solve to find. Okay, so a quick look at what's happening in terms of corrosion and how we can prevent corrosion from happening. So first of all, opposite of corrosion smelting is the industrial process of refining metals into their pure state. So we take a metal from its naturally occurring oxidized state and reduce it to an elemental form. So like for example, iron usually exists in iron oxide, but we smelt it down, get the oxygen out, so we have this pure iron. But that allows the metal to become oxidized, so lose those electrons. So corrosion can be viewed as the process of returning metals to their natural states, ores. And so an ore just means an iron combined with the oxygen. In corrosion, the metal is oxidized, causing the loss of structural integrity. And so, you see that in car bodies where the iron in it is breaking down. And over time, the frame is obviously not as sturdy. In terms of what's happening here, if we look at this in terms of the chemistry standpoint, this reaction that I've highlighted on your reduction half reaction table is the reaction between water and oxygen. So this is naturally occurring in the environment all the time. And this would then be a oxidizing agent. Anything below it then on this right side is susceptible to lose electrons to this reaction so it can occur. So if we look at this now, these are all SRAs, right? Iron is pretty low down here. So any metal here, so lead, tin, nickel, cobalt, iron, zinc, all of these are below this environmental reaction between water and oxygen and will willingly donate their electrons to this reaction. So this reaction occurs naturally without any sort of environmental input, right? That's kind of like a voltaic half cell. It will occur spontaneously. So just to kind of, I guess, reiterate what I said, corrosion is an electrochemical process in which a metal reacts with a substance in the environment, returning the metal to an ore-like state. And so, right, sorry, wrong way. Iron here would give up its electrons for this reaction to happen, and then I would have iron ions, which would more than likely combine with oxygen in the atmosphere. That's how we get that ore. So oxygen is usually the oxidizing agent, and as we've seen in the reaction there, it has to be combined with water for this to happen. Gold and silver are weak reducing agents, so we don't actually see those corrode. That's why we have a lot of jewelry made out of gold and silver, because they will not break down or corrode over time. If we look at this chart, right, gold is up here and silver is right here. So these are non-spontaneous reactions. The only way that these would corrode naturally is if there was some sort of input energy or input voltage causing this reaction to occur. So remember, these are not spontaneous because these RAs are above this reaction as an oxidizing agent. And there is just, I guess, looking at the two half reactions that would be happening between iron and oxygen and water. So oxygen is reacting with water and the electrons at what is essentially the cathode, and the metal, which is breaking down into the metal ion as well as giving up those electrons, is considered the cathode, right? This is a losing electrons, so it's the anode. Gaining electrons, cathode. Most metals develop a thin oxide coating which protects them from further oxidation. So you see this especially with alkali metals. If you cut an alkali metal, such as lithium, let's say, it will automatically very quickly create a oxide coating, which prevents this further oxidation. However, eventually this oxide coating scales off, and the new layer below it is more susceptible to corrosion. Salt will speed up these oxidation reactions by acting as a salt bridge. So once we have that sodium in the water, we have an easier transfer of electrons for anions and cations to move back and forth. So this is a spontaneous reaction, pretty much just what that is saying. Corrosion prevention. Now, let's just first of all look at the different types of corrosion prevention. Sorry, I'm going to go really quick here. My daughter is also sick and not feeling very good, so bear with me. Corrosion prevention can come in two or three different ways here. The first one would be looking at protective coatings, so such as painting different polymers or encasing the metal in a different object. Generally, this is pretty simple, cheap, and cost-effective, but eventually we have chips and cracks, right? Like, look at our vehicles, we paint them, but over time the paint wears off, and if the paint wears off and you don't get it fixed right away, that iron is exposed and can rust really quickly. The second method here is cathodic prevention, where, let's say, for example, we have a pipe made of iron. If iron is exposed to oxygen and water, it's the strongest oxidizing agent, the strongest reducing agent. It's the anode. It's going to give its electrons to water and oxygen. So in order to prevent this from happening, that corrosion of iron, because if it corrodes and whatever's in the pipe leaks out, we have problems. So in order to prevent this corrosion, we attach another metal that is lower on the table than iron, and that then becomes the reducing agent, and so it is the anode. So if I look at this again, so we make a pipe out of iron, let's say, and if I attach a piece of zinc or a large piece of magnesium, aluminum, whatever it is, to it, these metals would then act as the anode rather than iron itself. So iron would be protected, and these would undergo this reaction, donating its electrons up to this water and oxygen reduction half reaction. And so here's kind of an example. If we have a steel tank underground, they are generally connected by a wire to magnesium, and like we said before, magnesium is below on the chart. So it will react rather than the tank itself with the water and the oxygen, and so we have what's called cathodic prevention, and the magnesium is the sacrificial anode. Okay, my daughter's in full panic mode here. If you need to go through this, there is a little bit more information in the textbook, as well as on this PowerPoint for you. I think that should be enough information for you to finish homework 8 or 9, and do the next homework in the book as well. Let's just take a quick look at what the homework was. So finish up questions in homework 10 here that you didn't do yesterday, and homework 11 then you should be able to answer based off of what we just looked at. Thanks guys, have a good one.